Texan Global School. Operations with algebraic expressions. Division. We will begin by remembering the definition of fractions, which indicates that, for every number a and b that belongs to the set of real numbers, if b is different from 0, we can see two ways of representing a divided by b. The quotient can also be expressed as a times b to the minus 1 by laws of exponents. We then identify the dividend as a, and the divisor as b. There are three general cases to perform divisions between algebraic expressions: dividing monomial by monomial, dividing polynomial by monomial, and dividing polynomial by polynomial. It is important to have and understand the laws of exponents, analyzed in previous classes, to be able to perform these types of operations. On the other hand, we will remember the sign rules of division. Plus divided by plus is plus, plus divided by minus equals minus, minus divided by plus gives minus, and minus divided by minus gives plus. In short, the quotient of equal signs is positive, the quotient of different signs is negative. We will start with the first case of monomial divided by monomial. These types of expressions are performed and simplified using the laws of exponents. Let's look at some initial examples. The quotient a divided by 2a, using the definition of fractions, can be represented in two ways, as shown in the example. The 8 can be represented as 2 cubed. All bases without an exponent, by definition, are raised to the first power. Now, using laws of exponents, we will move the factors of the denominator to the numerator with the opposite sign. Now, we group equal bases and subtract exponents to simplify. We thus obtain 2 squared, a raised to 0. By definition, a raised to 0 is 1, so the result of this division of monomial by monomial is 2 squared, or 4. To perform the operation of 11b cubed divided by 121b to the 5th, we will first transform 121 as 11 squared. Then, we will move all the factors of the denominator to the numerator with the opposite sign. Now, we group equal bases and subtract exponents to simplify. Obtaining 11 raised to the minus 1 times b raised to minus 2. By laws of exponents, the result is 1 over 11b squared. In this next example, we will also perform the operation of a monomial divided by a monomial. We represent the expression as a fraction according to the definition. Now, using the laws of exponents, we multiply the numerator by all the denominator's factors but with opposite sign. We group equal factors and add or subtract their exponents to simplify. Finally, since we have negative exponents, we will move them to the denominator using the laws of exponents, expressing the remaining polynomial with positive exponents. We obtain, as a result, 3y squared over x to the 4th z. In the third example, we can see that the numerator is not a polynomial. Since it does not meet the definition seen in previous classes, one of its literal factors contains a radical. However, the operation can be performed in the same way, but including laws of radicals. We will prepare the expression by transforming radical factors to factors with bases with fractional exponents. We also represent those bases raised to the first power. We can also see that we must start with the order of operations. That is, we will first perform the exponent of the denominator, and then the quotient between algebraic expressions. Once the exponent of the denominator has been performed, by multiplying exponents, we represent the operation as a fraction. We multiply all the denominator factors with opposite sign by the numerator. We group equal bases and add or subtract exponents to simplify. Remember that the results must be expressed with positive exponents and radicals. Therefore, we move those factors with negative exponents to the denominator, and transform fractional exponents to radicals. Thus, we obtain a result of 1 over 49x squared, times the square root of y to the 17th, times z. We will then go on to the second case of division, polynomial divided by a monomial. Using the laws of exponents and the property of fractions below, we will perform this type of operation. This property is based mainly on the distributive law. It indicates that, for every number a sub 1, a sub 2, a sub n, and b, which belong to the set of real numbers. If b is different from 0, the quotient of a polynomial by a monomial is obtained by dividing each term of the polynomial by the monomial as shown. Let's look at the first example. We will perform the operation of a polynomial between monomial. We sort in descending order and/or alphabetically, both dividend, that is, the polynomial, and divisor, the monomial. Using the property of fractions, we separate each term of the dividend by the divisor. It is important to consider the signs rule for division. Because the denominator is positive, the signs of each term in the numerator do not change. We then apply the laws of exponents to simplify each term. We can see that the process changed a little bit, because we have more practice with laws of exponents. Instead of moving all the denominator factors to the numerator with opposite sign, we analyze which one to move so that, when simplifying, it gives us the result already with positive exponents. In the first term, we move only a to the numerator, as a to the minus 1. We do not move 3, since the numerator does not have a factor of base 3 that can be simplified. In the second term, we move all the factors of the denominator, since we have a single base of each factor to be simplified. Thus, we obtain minus a over 3, plus 1, minus 1 over 3a. As we initially ordered, the result is already in descending order. We can repeat the previous process where we move everything to the numerator with opposite signs. And later, we move to the denominator those bases with negative exponents. However, due to the practice from laws of exponents, laws of radicals, and multiplication between algebraic expressions, in previous videos, we can make other ways to make processes more efficient. In this other example of a polynomial divided by a monomial, we alphabetically sort the literals of each expression, and the numerator in descending order. Then, using the property of fractions, we separate each term of the dividend by the divisor. It is important to consider the signs rule for division. Since the denominator, that is, the monomial, is negative, all the signs of each term of the numerator change. After separating each term divided by the monomial, and changing the signs, we separate prime factors to identify equal bases. The 10 in the second term, for example, is separated as 2 times 5. The 20 in the third term is separated into the prime factors 2 times 2 times 5. And the 45, as 3 times 3 times 5. Then, we apply the laws of exponents to simplify each term separately. We can directly cancel 5 out of 5 in the first term. Instead of using the laws of exponents by moving the 5 of the denominator to the numerator as 5 to the minus 1, and adding the exponents, obtaining 5 to 0, which by definition is 1. Hence, as the laws of exponents have already been analyzed, we can make the process more efficient by simply canceling identical factors. In the second term, we can also cancel 5. In the third term, we cancel 5xy, since they are identical factors in both the numerator and the denominator. In the last term, we cancel 5z squared. We then continue to simplify each term as a monomial by monomial, using the laws of exponents. In the first term, we move to the numerator x and y as x to the minus 1, y to the minus 1. We then move to the denominator z, as z to the minus 1. In the second term, we move to the numerator x, as x to minus 1, and we move to the denominator z, as z to the minus 1. In this case we cannot simplify y, since there is no other factor with the same base. In the third term, we lower z as z to minus 1. And in the last term, we move to the numerator y, as y to the minus 1. As we already simplified real factors, we simply multiply those that were left with different bases. Finally, we add or subtract exponents. And we obtain an already ordered result of minus x cubed y squared over z plus 2x squared over yz minus 4 over z plus 9y over x. The last division case between algebraic expressions is polynomial divided by a polynomial. Gobrin proposes an algorithm to perform the division between polynomials. It is done by sorting both dividend and divisor in descending order. If any term is missing from the dividend or divisor, it must be represented as 0. Then, divide the first term of the dividend by the first term of the divisor, thus obtaining the first term of the quotient. The first term of the quotient is then multiplied by each term of the divisor. The resulting polynomial is placed, ordered, below the dividend. These polynomials are subtracted to obtain the new dividend. And the process is repeated, now considering the new dividend. Let's see a first example of this case. We will represent the given operation as a fraction to clearly identify the dividend and divisor. We order each polynomial in descending order. We can see that all the terms are complete, so it is not necessary to add zeros. We put the dividend inside the division bracket symbol and the divider outside. Now we take the first term of the dividend and divide it by the first term of the divisor. That is, a squared over a, thus obtaining a. This is the first term of the quotient which is placed on the division bracket, in the corresponding column. In this case, on the column of linear terms. So, we multiply this term of the quotient a by each term of the divisor, obtaining a squared minus 2a. We subtract this polynomial from the divisor, which implies a change of signs in all its terms. We obtain then 3a, and we lower the next term which is minus 6. We thus obtain the new dividend. Hence, we repeat the process. Now, we take the first term of the new dividend, 3a, and divide it by the first term of the divisor, a. We obtain 3, which is the next term of the quotient. It is placed in the corresponding column. This term 3 is multiplied by each term of the divisor, obtaining 3a minus 6, and is placed under the new dividend. The polynomials are subtracted, and we obtain, in this case, 0 as a remainder. In the following example we will repeat the process. After sorting polynomials, we put the dividend inside the division bracket and the divisor outside. We take the first term of the dividend and divide it by the first term of the divisor, thus obtaining x squared. This is the first term of the quotient, which we put above the division bracket, in the column of quadratic terms. We multiply x squared by each term of the divisor. Then, we subtract the polynomials obtaining the new dividend. In this case, we repeat the process 2 more times, obtaining a quotient of x squared, plus x minus 2, and a remainder of 0. Texan Global School. Global online learning. Knowledge for the world. www.texanglobalschool.com